Okay, good morning. 15 minutes to go. We will look at the two examples for AC power. Okay, and then, well, let's bring it up right now. Last notebook. Okay, example one is a two-in-one problem. The reason I say that is because the first half requires you to solve for the voltage and currents. Okay, so the problem has uh, a RLC components, and the question being asked is determine power for every single component. Okay, so when we look at those, we have R, resistor R, inductor L, and capacitor C, RLC circuit. You have an AC voltage source being applied. Now, when it says every single component, even if it does not state the source explicitly, you do have to find the power for the source also. Which, of course, if you find power for all three, law of conservation of energy applies, and then all the power that is being received by the three components has to equal the power being delivered by the source, right? So we have to find power for all four components in there. Okay, the source and the resistor, the inductor, and the capacitor. Now, think back to chapter 1 and 2. If you have a resistor, which are the three equations we come across? Ohm's law and the power equation. Ohm's law is V equals IR. Power equation is product of the voltage and current. P equals VI, right? Similarly, for an AC circuit, we do need the voltage and the current, or the current, if you wish to find the power for any component, whether it's P or whether it's Q. So first half of this problem requires you to do AC analysis, meaning you determine the voltage and the current for the components, and then we can go into the power. And hence I said two-in-one problem. So let's take a minute, go through the initial part of the solution, and then we'll proceed. Okay, so now that you have written down the circuit and some equations, and hopefully have had time to look through this and think about it, what do we see? First step, of course, is to draw out the equivalent impedance diagram, right? We want to make sure everything looks like a resistor. So we draw out the equivalent impedance diagram. So now you have a voltage source and three impedances. Inductor is replaced with ZL, capacitor replaced with ZC. And R, of course, remains exactly the way it is. Then we note the current coming from the source as I. Source current always goes from minus to plus. And we can see the current goes through the inductor. So inductor current IL is the same as the total current coming from the source. Reaches the junction and splits in two. So we can apply KCL and state I is equal to IR plus IC. Right? Total current coming from the source goes through the inductor and then splits between the resistor and the capacitor. Then our job would be to find ZEQ as seen by the source. ZEQ as seen by the source, VS. Think back to chapter 2. When you have a resistive circuit and it is possible to reduce the entire circuit down to one single resistance, we find REQ. So it's the exact same approach. We have multiple impedances in the circuit, and it is possible to reduce the entire circuit down to one single impedance. Remember, the goal is to find all the currents and all the voltages for every single component. Okay, so you can use a multiple, variety of techniques. You could apply node voltage analysis if you wish, mesh current analysis if you wish, but there is no need to do so. Right? This is a far straightforward and even simpler circuit, all things considered. There's only one source in here, and it is possible to reduce everything down to one single impedance. So that is the approach we take. So starting from the top, the next step would be to combine the resistor and capacitor into a single impedance. Remember, we cannot add a resistance and a capacitance, but we can add the impedance of the capacitor to the resistor. So R and ZC in parallel, I note it as ZRC. ZRC is the equivalent impedance of the resistor and the capacitor in parallel. Okay, so R parallel ZC gives me ZRC, and then ZRC would be in series with ZL. That gives me one single equivalent impedance, ZEQ, ZL plus ZRC. Now what I've done here is, without using any numerical values, I'm determining the equation for ZEQ. And I would recommend students do the same. Before plugging in any values, especially when we are working with complex numbers, it makes it easier and minimizes errors if we find our equations first. So now that I have my equations, I can go ahead and look at all the numbers. But let's take a pause, think over this, and let me know if you have questions. All right, any questions? So far, so good. Does it make sense, the approach? Okay. All right, then let's go over to the numbers. Take a look at the voltage source, because everything comes from the source, right? So in this case, we have a voltage source. Voltage source is given as 10 sine 1000 t. Because it's sine, the first step we do is convert to cosine. Convert to cosine. Sin x is cos of x minus 90. We subtract 90 degrees from that expression. So we get 10 cos 1000 t minus 90 degrees. Then we equate it to the standard expression, extract information about Vm, the peak value, omega, as well as the phase theta. Once you have those three, we can write the phasor for Vs directly. Remember, we're using complex numbers, so everything is expressed as a complex quantity. So phasor Vs is 10 with an angle of minus 90. Then we have omega, so we can now calculate ZL and ZC. Okay, ZL and ZC. And here, I will determine ZL and ZC both in rectangular coordinates as well as polar, because I know that I'm going to perform addition as well as multiplication and division. So it makes things easier to have everything before we begin. So ZL, of course, in rectangular coordinates is j omega L. In polar coordinates, it's omega L with the angle of plus 90. Remember, Eli the Iceman, voltage always leads the current. So in inductor impedance is always plus 90. Capacitor impedance is always minus 90. That doesn't change. Okay, standard equation for a ZL in polar coordinates is omega L with the angle of plus 90. ZC is 1 over omega C with the angle of minus 90. 1 over j omega C. 1 over j is minus j, which is minus 90. Chapter 5, Eli the Iceman. Okay, these are standard expressions, standard equations. So once we have those, we have the values for the inductor and the capacitor impedance. By ZRC, two components in parallel. So again, going back to chapter 2, two components in parallel, product of the two divided by the sum of the two. So R times ZC divided by R plus ZC. R times ZC. R is given as R is given as 100 ohms. In polar coordinates, you can write this as 100 with an angle of 0 in rectangular coordinates plus J0. Right? Resistance doesn't have any phase difference between the voltage or current. Always lies flat on the x-axis, 0 degrees, with respect to its current, I mean. So resistance is 100 ohms. And when you plug it into this expression, perform your calculations, and you end up with ZRC with these values, 50 minus J50 ohms. Okay. That is just the resistor and the capacitor impedance together. Once you have ZRC, add it to ZEQ, add it to ZL to determine ZEQ. Remember, we already have the equations. All we are doing is plugging in the numbers. Again, derive the equations first, then plug in the numbers and perform your calculations. And once you have ZEQ, apply Ohm's law. Remember this diagram right here. Vs, the source is supplying current I to ZEQ. So I is Vs over ZEQ. All right, questions? Questions about the approach, about the calculations? Yes. The ZRC is the resistor and capacitor in parallel. And so it would be 1 over R plus 1 over ZC, and then the reciprocal. No more questions? Does the approach make sense thus far? Okay. All right. We'll end class here today. Pick up here on Wednesday. Please make sure you go through examples 1 and 2 before coming to class. Just spend 10 minutes, 15 minutes tops. Okay. Review both the examples from the class notebook so you're better prepared to ask questions. Okay. Big quiz next Monday. Big quiz next Monday. So prepare accordingly. And I'll be in my office later on this afternoon. Please stop by with any questions you may have.